So, assalamu alaikum, Molweni, good evening, Khoyanant, all the attendees. Thank you for joining us today. My name is Tokir Ahmed, and this is the SAICE Fireside Chat in collaboration with the SAICE Academy. And thank you for joining us with us today. Welcome back to another episode. It's our second one for the year, and we've got a lot in store for the year. And we hope that today's topic will be thought-provoking for you. For those who are new to this platform, welcome. Thank you for joining us. So just to give you a bit of insight, these discussions are aimed at stimulating debate and discussion around civil engineering, innovation, smart technologies, whatever may be of mutual importance to us as civil engineers, and engagement and collaboration with the other fields as well, because we're not only just a single discipline. We get involved with mechanical and electrical engineers, so we just need to make sure that we also align and collaborate with them as well. So we normally host and run these on the second Thursday of every month. So again, if you are new, keep an eye out for that and do expect something same time, same place, second Thursday of every month. And yeah, so typically what we have is we have a matter specialist, and will come and present. And then we have a panel discussion, followed by the discussions. So for yourself as we want yourself as the audience to also engage. Put up your hand, come talk to us, put your comments in the chat box. So yeah, I encourage you to participate, and let's just make this a debate and a discussion. So yeah, we also want you to then rate your experience. It helps us to give you content that is more focused to what you want to see, and plus to make sure that we are at least delivering what is then expected. So yeah, I'll drop in a link in the chat soon to the survey questionnaire. If you can then fill that out for us, and it's much appreciated. So today, the topic for today is now the South African Plastic Pipe Manufacturers Association, or SAPMA. They are a non-profit body representing, leading manufacturers of plastic pipes in South Africa. They have been instrumental in setting and maintaining high standards in the plastics industry, plastic pipes industry, specifically in South Africa. So they also ensure, quality, sustainability, responsible manufacturing of all plastic pipes. They promote best practice and provide technical expertise, and also engage in research and development within this field. And as you would know, thermoplastic pipes, they're quite, versatile. You can heat them up, you can mold them into any shape. So very versatile, especially for us as civil engineers. We need certain pipes for certain, applications. And so, yeah, I guess from SAPMA's point of view and pipe manufacturers, they've got all that we need. So today, we've got a colleague from SAPMA. So Katiso Lapo. I think if we can just ask yourself to come and introduce yourself and then Jan. So Katiso, just a quick introduction. Just tell us who you are, what you do. I think we can also then test your camera and mic. Hi, Katiso.
Hi, can everyone see me? Good
Yes, we
afternoon.
can see you.
My name is Katiso Malapo. I'm a member of SAICE. I'm also a member of SAPMA. I'm a civil engineer, and also specializing sometimes in structures. I studied civil engineering at Wits University. I got a BSc degree from Wits University. Then I went to study a master's in civil engineering at Stellenbosch. So I have over 20 years of experience working in the field. Actually, the reason I need to clarify this because I graduated at Wits in 2006. So I studied at a technicon before I went to Wits. So at the time I had already had about 4 years of experience before I resigned and went back to studying. I'm a member of SABS subcommittee that's responsible for reinforced concrete structures. I'm also a member of a working group that is associated with the same subgroup that is responsible for coming up with a new standard for South Africa for liquid retaining structures. I'm a member of academic advisory committee at TUT, Tshwane University of Technology. So as I said, I'm also a member of SAICE. yeah, I have also designed a reservoir, some reservoirs for Ekurhuleni. Yeah, and I reside in Johannesburg with my family, my wife and 3 children.
Yeah. No,
Thank you.
that's awesome. That's awesome. Thanks, Katiso. And yeah, look, I think you raised quite a few things and potential topics for the future. Perhaps we must maybe cover reservoir designs in one of the future episodes. But yeah, let's engage offline and then look at the other topics. But no, you've got quite a wealth of experience out there. No, thanks, Katiso.
Thank
Jan,
you.
if you can just also come through and let's introduce yourself, Jan. Uh,
Hi, yes. Thank you, Taki. Can you hear me? Is it all okay? Yeah.
yes, we can hear you.
Yeah. All right. Yeah. Thanks very much for the invitation and the opportunity to talk to you guys. I'm the CEO of SAPMA, civil engineer, professional engineer for many years, and I've had too many years experience in this industry than you'd like to know. Certainly, it's more than 40 years. So well versed in it, I think, and I hope. And yeah, we'll be available to answer questions at the tail end of the presentation. I'm sure. And yeah, so let me hand back to you, and thanks again for the invitation.
No, thanks, Jan. Thanks, much appreciated. Great to hear that that wealth of experience that you do have, and hoping colleagues online, do ask those technical questions or deep questions. The knowledge is here, the experience is here. Let's take advantage. No, thank you. So I think then what we can do, we can then start, with the presentation for the day. Katiso, so just before Katiso comes on the colleagues, we were supposed to have Mike Smart. Mike Smart was supposed to do the presentation. Unfortunately, he's taken ill. So yeah, we just wish him the best. And yeah, so Katiso is here in his place. So Katiso, if we can then hand over to you, if you can just put up the presentation.
Thank you. Do I need to have the camera on?
No, you can put the camera off. Yeah, I'll also put this. We need to save bandwidth.
Yes. Okay.
One day when you get super fast 5G or 6G, can have a camera on. Okay, let me just do that.
Okay, let me look for the window.
Okay. Okay, if we can just put into presentation mode.
Yeah. Can you see it now?
Yes, we can see it. Just to put in presentation mode.
Yeah. So is it not in presentation mode now?
No, we just see the slides.
Okay, let me just do this because I'm sharing because I couldn't connect directly from the thing from my MS Teams. I'm sharing using the internet.
Okay.
So let me see what.
Otherwise, if you're struggling, then we can make a plan with the other view as well. I think we can run with that also.
Can you see it now?
Yeah, it's still the same screen, but I think that let's continue. Yeah, there you go. We got it.
Yeah.
Yeah.
Okay.
If
Yeah.
we can just
So
have a few thumbs up from colleagues just to say confirm that you can see it from your side as well. Okay, perfect. Off you go, Katiso. Thanks.
Okay, thank you very much, Taki, and thank you to SAICE for inviting us. Today we're going to talk to you about thermoplastics because this is not considered a traditional civil engineering material, even though it is actually a civil engineering material. We are more familiar with cement, soil, crushed stone, concrete, and steel. And even timber. But whenever it comes to plastics, to most of us, it usually comes as if it's usually considered like a foreign material. We sometimes have specifications where people are specifying the black PVC, which is actually a black HDPE. So I want to take you through the differences in the two materials, and perhaps even expose you to the more information that you can collect or acquire on your own from our website, SAPMA. So you've actually done a great job in introducing SAPMA, and you were very correct in everything that you said. We have members that we are representing, who are manufacturers of plastic pipes, and we also represent all other stakeholders who are in that plastic pipe value chain, like suppliers of raw materials and other converters. So if you were to go to our website, which is www.sapma.co.za, we have a technical manual. It's on the 5th edition now. From that manual, you can actually download it, and from that manual you can get much more than what I'm going to show you today. Because we have limited time, we'll just focus on a few things, just to excite you and even to make you aware of certain differences between traditional materials and plastic pipes or thermoplastics. So why are we here today? We currently have a serious problem. Actually, I would say it's a nationwide problem. I'm sure you are well aware that South Africa is a water scarce country. Gauteng or Johannesburg, for instance, is sitting on a watershed, and we can't even store water here. The nearest place we can store water is the Vaal. And for us to get that water, it has to be pumped all the way. I think it's almost 100 kilometers, and pumped in 2 stages until it gets to reservoirs. Then it gets distributed to various municipalities. Apparently, in Johannesburg, they lose about 50% of the water that they receive from rainwater. This is not only Johannesburg. Other municipalities are a little bit lower. But you can imagine if you are collecting that water or you are buying that water from rainwater, supplying you at a certain rate, and then you have to sell it. The profit that you are going to make now from 100, you still have to pay for, let's say you bought 100 liters of water, you have to pay for 100 liters of water, even though you are now left with 50 liters to sell. That cannot be sustainable. So we as SAPMA, we have decided to come forward and offer our help. We know that there are a lot of other things that can be causing all of these problems. So while those things are attended by the people who know how to address them, we as the know-how of plastic pipes, we can offer our help so that at least this losses can also be reduced. But at the same time, as SAPMA, we were on the road show to more like reintroduce ourselves to the industry, and make ourselves known to the civil engineering industry, because we felt that the people who were actually doing the specifying of products and even designing were not really aware of the difference between what SAPMA member, who the SAPMA member is, and what they can actually do. So this is our first stop in that roadshow. In fact, previously we have already done in the past year. I mean, this is our first stop this year. But in the past 2 years, we've also presented to University of Pretoria and even Wits University. So we asked the question, why are we here today? So we are here because of the water crisis in Gauteng. Over and above the other things I've told you, up to 50% of water is lost. There's also aging and failing infrastructure. Our only hope is the Lesotho Highlands Water Project Phase 2, which has also been delayed Other people are speculating that it will be completed around 2030. Others are saying beyond that. So SAPMA is here to offer help through training and technical support. So let's go into plastic pipes. So there are two main types of plastics, thermoplastics and thermosets. Thermoplastics are plastics that change, they become soft with increasing temperature. As the temperature reduces, they become harder. So you can either heat them and make them soft and mold them, as you were saying previously, and you can reverse that molding and reshape it into a different thing. But you cannot do the same with thermosetting plastics. Once you expose them to heat, they harden. And the reason they harden is because they have cross-linked chains, and which also have a 3D molecular structure that disintegrates under heat. So once you do that, the whole thing becomes hard. Whereas with the thermoplastics, they are uncross-linked chains, and we can heat them up to soften them, and also cool them down to make them hard. Examples of this thermoplastics are polyethylene and PVC. So these are the two main materials that we are going to be talking to you about. And we have to stress the point that we want to distinguish them from the normal thermoplastics, in that this type of plastics are called noble plastics. So whenever I'm using the word noble plastics, you need to know that I'm referring to the thermoplastics that are the polyethylene and polyvinyl chloride. And there's also other ones like polypropylene. And then we are calling them, I want to make this distinction is to separate them from commodity plastics that are used for packaging, which are sometimes responsible, or maybe or most of the time responsible for pollution and the microplastics issue that we are always hearing about in the news and on the internet. So why they are novel plastics? By definition, they are high performance. They have a high performance. They're durable. They're chemically stable polymers. They are also very superior to commodity plastics in that they have long-term reliability and resistance. In fact, they're designed for a lifespan of longer than 50 years. So they also work, they play a very important role in infrastructure development because of their longevity, efficiency, and sustainability. So you can recycle 100% of these plastics. So why are we considering the two of them, HDPE and PVC? Both of these materials, although different, they are durable and they have longevity, meaning lifespans of 50 to about 100 years. So you can actually use them very well over a very long lifespan for your infrastructure development, and they are resistant to chemicals and corrosion, which means that they are ideal for clean water storage and industrial applications, including acid mine drainage. So they also have very smooth surfaces, making them to have good hydraulic efficiency. Their strength to weight ratio, they are light but very high strength to weight ratio. They are very light, but the mechanical strength is relatively high. In terms of sustainability, they are 100% recyclable, and they play a very important role in the circular economy. So how do this behave? So noble plastics like PE polyethylene and PVC are like you and me. So in that, they have a unique footprint. They also have a working life. So we know that we have a certain life expectancy from when we are born. Same way, they also have the same things. As they grow old, they regress, meaning the strength that you will test or get from the lab today, as that pipe is in use, that strength will be slightly lower after a long time. But we'll show that that's where the creep rupture regression curve comes from. The CRRC that you're seeing there is a creep rupture regression curve. So which shows that the strength declines with age. So they are also temperature sensitive. Like a baby, when they are cold, they will sneeze, or even a middle-aged person or an old person. When we are very hot, we want to take off our clothes. Same thing happened, but in a slightly different way. In that, when temperature rises, they become soft, and even the strength reduces. But when they become cold, then everything goes back or reverses. So they have to be used for a particular application. For example, if you have seen HDP, which I will show the pictures of, the black one, the good thing about it is that you can use it above ground, and what it has in there that makes it to be black is carbon black. So this carbon black makes it to be resistant to UV rays. You can't do the same with normal PVC, even though it has some stabilizers in them to help protect it, but it's not as resistant to UV rays as polyethylene. So you can't just use it anyhow you like. And these materials are not like other materials. They have variable attributes. You have concrete, whether it's hot, yeah, there are some changes that you can get in concrete, but they are very small and negligible. But in plastic pipes, any change can be seen with varying time or changing temperature. So they also have superior attributes in the short term. They can be used in certain niche markets like slurry conveyance because of their good hydraulic properties and abrasion resistance. So they also have less environmental impact in that you can recycle them. Some of them, some standards allow the use of recycled material in them, like multi-layer PVC. They call it foam core. That uses a recycled foam as a like sandwiched between the two solid PVCs on a pipe wall. So what's with this HDPE? So the HDPE that we are talking about is classified as PE 100. So the classification is that 100. It's a high density, stands for high density polyethylene, and it's made by polymerization of ethylene, which is a feedstock derived from production of oil or gas. So with it, it comes out as a powder, but it has to be compounded at a place where it's made and pelletized. So as you do this, you add the additives in it. So they can come in different colors depending on what you are going to use it for. But for plastic pipes, you get a color black, which has carbon black in it, and it's resistant to UV rays. But at the same time, you can get an orange PVC HDPE pipe, which is for gas applications. So companies like Sasol Gas or Egoli Gas use the orange HDPE. The additives or stabilizers also help to protect the pipe against heat degradation, as we have shown that it's very sensitive to temperature. So there are certain additives that are added into the thing to reduce the rate at which it deteriorates or degrades due to heat. The standards that are applicable for this, ISO SAICE 4427, it has several parts, and also ISO SAICE 4437. So the 27 is for water and the 37 is for gas. So the picture that you're seeing there is an example of one of the pipe that's made to 4427. So it's recyclable and lighter than water. What this means is that if you were to install it in a swampy area or where the water table is high, you have to be mindful of the fact that you're going to have to deal with buoyancy or flotation, meaning that you now have to resort to your traditional civil engineering material, which is concrete, to hold it down. So usually they will make clamps, or some people mix. I saw in Germany where they mixed a slurry and hold the thing in place until the slurry sets. So there, where the pipe goes through the thing, even for sewer outfalls into the ocean, HDPE will float if you don't hold it down, just because of this specific gravity that is below that of water. PVC, not all pipes or plastics are PVC. So we sometimes see in specifications that they have asked for a PVC, a perforated PVC. I think they used to make it a long time ago, but now if you specify perforated PVC that is black, usually the person who was specifying actually meant corrugated HDPE. So because maybe they are not aware of what the word PVC means, they would take anything that is plastic to mean PVC. Maybe the confusion comes from the P in the PVC. So it stands for polyvinyl chloride, which is also derived from oil, but here you also have salt. So you have salt water that is taken through a reactor or a process that will produce chlorine. Then that chlorine is added to ethylene. Then it produces vinyl chloride monomer. So in the same way as the other one was producing a monomer, and then you have to polymerize it. By polymerizing it, the word poly, which means many, you are now forming it into many chains. That's how it becomes polyvinyl chloride. It's sold as a powder and then mixed at the factory with additives. Unlike HDPE, where at the place where the raw material is made, they will mix everything into it so that it's just ready to be placed or added into the machine to be manufactured. So the types of PVCs that we have, some of them, or the main ones that we are using for civil engineering and municipal services, it's a PVCU, where U stands for unplasticized, meaning they haven't added plasticizers. The ones where they've added plasticizers are like the soft ones, like the PVC that they use for hoses. Or hose pipes. So you will see they are more flexible than the PVC the PVCU that you are using in civil engineering applications. Then you also have PVCM, where M stands for modified. It's the same thing as PVCU, but now they've added stabilizers or materials that improve its impact resistance. So the M is just to improve, and I believe it was made initially for the mines where they don't normally use thrust blocks, and you also have to anchor the pipes or maybe hang them underground where you can actually have thrust blocks. So they had to have that high resistance to impact forces. Then one of the later innovations in the PVC plastic pipe market is the OPVC, where O stands for oriented. So you take the same PVC, and then you stretch it in both directions, in the longitudinal direction and in the circumferential or hoop direction, to rearrange material, the molecular structure of the pipe in such a way that it will give you a higher strength. So standards that are applicable for PVC, even though I have not listed all of them. So for a pressure pipe, you have for PVCU, you have 966 part 1, PVCM, that's 966 part 2, and then you also have the last one as the standard for PVCO. All of them are 100% recyclable, and they are also slightly heavier than water, with very good properties for conveying water. So we've already said that these materials have a unique fingerprint like human beings. So each one of them has a rupture regression curve that have that particular formula, which has logarithms. So there will be a log scale in the vertical direction, and another log scale in the horizontal direction, showing the time. I will show the slides for how those regression curves look in the next slides. And the minimum required strength, which is the MRS, is determined at 438,000 hours, which is the equivalent of 50 years. Then in the future, there are people who are doing studies. In fact, maybe there are some materials already which can get to 100 years. You will see how those times are showing on the regression curve when I show it. So the minimum required strength is at 50 years. And remember, the materials are temperature sensitive. So you have to specify the temperature, which is like normal ambient temperature of 23 degrees. So how do you classify these materials? You have the allowable stress, which will be the MRS divided by the coefficient or design coefficient. So the design coefficient is more like a safety factor. In other languages, when you are designing concrete and other things, you also have safety factors. So the design coefficient C depends on the polymer attributes. So different materials or plastic pipes will have different C values, ranging from about 1.4 to about 2.5. So the lower the number, as you can see, if the number that you are dividing the MRS by is smaller, it will give you a higher allowable design stress. And they are stronger, tougher, and more ductile. But the brittle ones, or the brittle ones, will have a higher C value, meaning they reduce, or the allowable design stress will be lower for more brittle materials. So here is an example of a regression curve shown for PE 100. I will show you where the 100 comes from in the next slide. So you will see the lines there that are, you have different lines starting from the top, and then you are going down. If you were to look at the bottom left corner of your screen, you will see that each line corresponds to a different temperature. So as the temperature increases from 20 to 40 and 60 and 80, then your allowable or the hoop stress reduces. At the same time, you will see that the lower you go, or the other blocks, or where the strength is lower, you also get a more brittle mode, which actually goes hand in hand with what we just discussed about a higher C value giving you a lower stress. So here you have different PVCs. So the O, which has a higher strength. So you have O500. You also have PVCU and M, modified and unplasticized. And then at the bottom you have HDPE. So to get that 100 of HDPE, which is PE 100, you look at the green line, vertical line, which is 50 years on the log scale, and then the red one is 400 years. So you go to the to where your PE line crosses the green line. You will see, if you were to draw an arrow, that is the bottom arrow face pointing to the left, you get a value of 10. So to classify the way the classification works for these pipes, you take that value, which is the rupture stress, or the MRS, that minimum required stress, and then you multiply it by 10. So I will show in the next slide what I actually mean. So here is the MRS as you are reading it from the previous graph, which is the value of 10, and then you multiply it by 10, you get 100. So for PE 100, this is how you get to that classifications. In the past, we had a PE 80 and then PE 63. So the MRS for those two were 6.3 and 8 MPa. So we've already said something about how you obtain your allowable design stress, which will be the MRS, and then you divide it by the design coefficient. This is more like reducing the strength, so that when you do the design, you are working on a smaller strength. So for no gravity pipes, you also have a formula here where you can work out, or even any pipes will work out the ring stiffness. So where SR will give you the ring stiffness, E is the elastic modulus, and I is the second moment of area. Other people call it moment of inertia. And then the D, which will be the diameter. So then and the E will be the thickness, or maybe the effective thickness, because some of these pipes will come with ribs. So there's a way of calculating the ribs that are stiffening the pipe. So there's a way of working out that EN. The elastic modulus decreases with time. As we said, materials are the same as us human beings, in that with time they regress. and also E is also proportional to the classification. So as the MRS decreases, E will also decrease. So T, which will be the what you will work out as your pipe thickness, it's inversely proportional to MRS. So you calculate it using that, they call it a Barlow equation, where you take, you cut a free body of a pipe, and you assume the wall is a thin section, and then you resolve your forces, and then you should be able to work out the T, or the thickness, from the resulting equation. So for PVCO, you have 5 material specifications ranging from 315 to 500. So the 501, if you were to divide it by 10, you see the MRS for it will be 50. And the other one, the lowest one, will be 31.5, which, as you can see, is much higher than what we were seeing for HDPE. So we also have 3 design coefficients corresponding to various material classes, ranging from 1.4, or it's 1.4, 1.5, and 2. So in working out your allowable design stress for PVCO, you will use the design coefficient C to divide it by the MRS. So the pressure ratings also, they also have 5 pressure ratings for PVCO, which range from 10 to 25. Yeah, it's in fact it should be 25 bar in terms of pressure. So example of polymer classification for both PE 100, where the MRS is 10, and for PVCU, where the MRS is 25. In fact, the correct classification of that PVCU should be PVCU 250. But for PVCO, you have 5 material classification, 3 Cs, and 5 nominal pressures. So you have to be cognizant of the fact that for PVCO, you have those different values of C. So the strength attributes, as we have already shown, decrease with increase in time, or as time progresses, and they also decrease with temperature. So the strength attributes again increase with decreased time and decreased temperature. So meaning if you were to reverse the decrease in temperature, or even the time, the results, even though the time we can't, cooling, let me leave out the time, but cooling your plastic will reverse the attribute. So then you have creep, which is at constant stress, the strain increases. So unlike normal elastic materials, these ones are visco elastic, and with time, the graph, strain stress graph for elastic and viscoelastic materials, or noble plastics, is shown here. So with the elastic material, you have a very a constant slope, stress strain slope. Then you get a yielding and a small kink and strain hardening after that. But with the viscoelastic materials, you have under constant stress, which in the case of water, it will be a pressure inside the pipe, as time goes on, the material experiences relaxation, meaning that the strength goes down. That actually explains what happens to it with the time. That the regression that you saw on the graph, where with time your strength is actually going down. So derating of novel plastics. Here we are using the example of PVCO. So when they are classified or tested, the reference temperature that is used is 23 degrees C. So as temperature increases, the attributes decrease. So you see here there's a graph of temperature against, of a derating factor against temperature. So you have the derating factor on the vertical axis and temperature on the horizontal axis. If you go up the 20 degrees or around 23 degrees, you see where the derating factor is 1. So as the temperature goes below, but this was extrapolated, you can see the graph shows the strength or the factor going up, meaning the strength will go up. But as you increase the temperature above 23 degrees Celsius, your strength drops, or the derating factor goes down. So this is what you will multiply the strength by to get an idea of how the strength decreases as the temperature increases. So for polyethylene, the derating factors are on the vertical axis, and the temperature is there again. You will see the slope is a bit steeper, because this one seems to be more sensitive to temperature difference. Again, at around 20 degrees, that's where your factor is 1. So, but as you increase the temperature, everything drops following this equation. So your elastic modulus also for PE, you can imagine if the strength is dropping as the temperature increases, you can also expect the elastic modulus. So if, for instance, you were to install this pipe in Katu or and Sishen, or maybe up the north in Namibia, where the temperatures sometimes go above 40 or around 40 degrees, and you want to work out the elongation, at least you know that you have to take into account the factor that your elastic modulus drops as the temperature increases. So you also have the thermal expansion of PE that also changes. You'll see the change is not that significant from 0 degrees. In fact, our graph goes from minus 20 degrees, where it's 1.6. It increases slightly as the temperature increases, and beyond 40 degrees, you can see the rate at which increases just changes. So it goes up. So usually your PVC and HDPE or PE100, it's always advisable to use them below 60 degrees Celsius. Anything above this, they are special, or maybe you need to get advice, or there are special pipes like polypropylene, which can actually take boiling water. And there are also variations of polyethylene and variations of PVC that have special additives in them that enable them to go above 60 degrees. So the other pipes that are there in the market, you have structured wall pipes. These are large diameter pipes that you normally use for no pressure, like where there is no pressure, that is gravity, and even for sewer outforce. But the challenge with these pipes, because they are flexible and very large in size, you have to be sure that compaction around the pipes, even the bedding is done properly, even though the same applies to all other pipes, because not compacting properly can actually cause you problems with leakages in the future, or the material on the pipe sagging and then compressing the pipe. You can imagine when a pipe deflects where it's supposed to be joint, the joint can actually open up, and then you have issues with leakages. So it's very important to make sure that compaction is done properly. So the other material that we have is multi-layer PVC for sewer, which is also called foam core, which is an innovative material that uses recycled material within the wall of the PVC pipe. Then you have corrugated HDPE, which also has some of them have 2 layers. You have a smooth layer on the inside, and then on the outside you have corrugation. So these pipes are mostly used for ducting. You also get corrugated HDPE for subsoil drainage, where the same pipe that is corrugated HDPE comes with a hose on top of it. So here there was a picture. In fact, I wanted to show a picture of myself inside this pipe just to give you an indication of how big these pipes are. So this is a structured wall pipe. I took this picture in Germany at a factory where they were making them. This one is about 3 meters in diameter. So you can even judge by looking at the height of the person standing next to it. So they are quite large pipes, which I believe we already have them in South Africa, but they are not so common. But I see them replacing concrete pipes for sewer, not in a very not too distant future. These pipes are also good for areas that are underlain by dolomite, because you can weld them. So instead of having just a concrete pipe that has a seal, with this ones you can actually weld each pipe together. The other nice thing about them compared to concrete is that they are very light in weight, so they don't require heavy equipment to move around. So for the structured wall pipe, the gravity market is dominated by reinforced concrete pipes. So usually whenever you talk about the structured wall pipes to engineers, they will be asking you about how stable the pipe is and whether or not it can take loads. So you have to be aware that whenever you're using a structured wall pipe, you have to build the structure on site. That is, you have a pipe, and then when you get to site, you need to make sure that whatever is going to surround that pipe, the soil is properly compacted, and you build it properly to make sure that the pipe is supported properly. The same way that it is recommended in SANS 1200L or LB or LD, how you are supposed to be compacting your soil, your backfill. That's exactly how you're supposed to do it for SWP. For those people who are pro reinforced concrete, like to say that what they are giving you is a conduit and a structure at the same time. Sometimes this justifies that there is no need for proper compaction around the pipe, because the pipe can already take the load on its own, which I really believe is not a good reasoning to use, because you get roads that are uneven because the soil, when people are backfilling, the soil is not compacted properly because they believe that the pipe that they are using can already take the load. So you really don't need to build that structure on site. I believe you still have to build the structure, even though the pipe, the reinforced concrete pipe, is strong enough. So yeah, that's my opinion. I suppose next time when we have another debate, we can discuss it further. So the soil and pipe have to, for structured wall pipes, have to be one structure that forms the whole pipeline. So your soil mechanics and geotechnical properties of the soil very important for and embedment. I've already mentioned that you have to bed it properly. So you also have to follow the new SANS 2001 for road construction, and it has to be done properly. So for noble plastics, the standard Proctor, the force that you use has to be 22% of mod Ashto. For tenders, usually you have to specify a 95% maximum. So Casa-Grande SC classification specified 90% mod Ashto or mod, which is equivalent to a 95 standard. The pipe stiffness, not ring stiffness, is a measured value, which is also important when you are designing this structured wall pipe. You have to take into account the pipe stiffness as it's going to actually work with the soil structure that you are building on site. Same design charts that you are using for reinforced concrete pipe you use for structured wall pipes, but with the advantage that your flow characteristics are a lot better. So the coefficient of friction is lower, and as other plastic materials, the corrosion is zero. So sewage, actually, it's reinforced concrete pipes, so much that you actually have to line them with the same plastic. So I don't know why we don't build them with plastic from the beginning. So the foam core plastic as one of the innovative materials. Yeah, I'm just showing that's already being used in South Africa as a sustainable solution for sewage, and it's lightweight. The embodied energy is low, and it's very stiff. You do this while maintaining the structural integrity and reducing material usage. The other benefits of plastic pipes, and also with respect to sustainability, they play an important role, as we have mentioned in the beginning, in the circular economy. They are 100% recyclable, and their hydraulic efficiency is good. And in the future, they can also be used for hydrogen conveyance, which I think it will be a big thing. Even for new green energy projects, we can also use these pipes. We need also to address the misconception about microplastics in pipes. So the reason I was making a distinction of noble plastics in the beginning was to distinguish them completely from the commodity materials or plastics that are used, even though these commodity plastics can be called thermoplastics, but they are not performing at the level of noble plastics. So in conclusion, Noble Plastics, PE and PVC are like me and you. They have a unique fingerprint, which means each one of them has its own regression curve. Um, they have a working life. They grow old with time, as you can see on the pictures there. I wonder whether the term regress is the right one. Maybe we should just say they grow old, because it's as if, yeah, things go backwards. Temperature sensitive between hot and cold, and they are suited for a particular job. So also, they are unlike other materials. They have variable attributes varying with time and temperature, and they have superior attributes short term, and they have superior niche uses like slurry, and have less environmental impact, and they are recyclable. Yeah, I think that brings me to the end of the presentation. Thank you for your attention. And if there are any questions or comments, we are ready to respond to them. Thank you.
No, thank you, Katiso. Thank you very much. And I must say, quite an interesting presentation, and nice technical. One wonders now. Did you ever do chemical engineering or study chemistry?
No, actually, it terrifies me.
Yeah, yeah,
I've never studied chemical engineering, but I think over time I've learned
yeah, yeah,
the technicalities of chemical, of chemistry, but
yeah.
only for plastic pipes.
No, no,
So
for sure, for
anything
sure.
beyond,
Yeah,
beyond that, I wouldn't be able to. Yeah.
yeah. No, I think, look,
Yes.
what I'm trying to highlight, and it is quite interesting, and it's a message I like to sort of push and promote at each of my sessions, that you need to be more than just your core uh, you know uh, uh, qualification. In this case, for you to work in this industry, you needed to understand plastics, the behavior of plastics, the chemical property of plastics. And as you showed now, the very technical detail of, the how plastics behave under certain conditions and tests, and the different properties. I mean, that's more the field of, almost like a chemical engineer or some kind of plastics engineer. But I mean, you had to do that, in your field, just to show you how diverse civil engineering can be in the different industries. So yeah, no, it's quite interesting. No, well done on that one. So
100%. Yes. Yes.
yeah, okay. So colleagues, that was the presentation. Now we'll start opening up for questions and comments. So I've got a few from my side, and I think let's maybe bring in Jan, with yourself being in this industry for so many years, 40 years. And as SAPMA, you now obviously need to regulate the pipe manufacturing industry. Make sure that you've done the studies, you've got to know how the knowledge as a body, and you know what everyone needs to comply to. So from a quality assurance point of view, because I think at the end of the day, us as engineers, making use of these things, we want to look for that SABS mark on the pipes. We want to get that quality control, quality insurance, or some sort of assurance, at least, that the pipes that we are purchasing and installing are what we expect them to be. So as SAPMA, how do you ensure that your members adhere to high quality manufacturing standards? And then, yeah, I mean, how do you audit the industry? Maybe you can just maybe share that insight, Jan.
Thank you. Trying to say it as quick as possible or as short as possible. Well, first of all, the reason why SAPMA exists is because of that very reason.
Mm.
And the official or accredited certification that one would expect to be done on plastic pipe is not what's not been up to now. It's not been what it should be. And because it's such an important material, we try and emphasize that, and it's come out in the presentation as well. In infrastructure, plastic pipe plays a dominant role in water, sewage, and obviously gas as well, which is not a big one in South Africa, but still. So yeah, and that linked to the fact that it should last 100 years or more. One doesn't want to dig out pipes and replace pipes, particularly when it goes through a built-up area. It's a long-term material, and that really requires, if you think back about the regression curves shown earlier, that requires very special attention. So, let me first say that the pipe standards, the national standards that are used in South Africa, are based on international standards. So it's well proven over many years, well researched, and if one sticks to the standard, you will get a 100-year pipe, within the framework of its application. So what we do as SAP to try and enforce that, we differentiate between manufacturers that stick to standards, 100% conforming to the standards, and those that are not. And in order to do that, well, first of all, that's obviously required of our members. To do that, we've got a very strict code of conduct, and that gets updated and even tightened on almost on a yearly basis. So members have got to comply to that code of conduct, and that includes a whole host of requirements. What we do to enforce that is that, or to check that, monitor that, is that we have regular factory audits of members. Those audits, very importantly, are unannounced, so they don't know pull out a sample and have it tested. We get it tested by an accredited lab, independent lab. So what the information or the results that you get, you can rely on. So we do that, and then of course we've got also a few additional standards that we apply to our members over and above the national standards. One can go on and on, Takir. I don't know whether that answers the question in part. We can elaborate on that, but I don't think it's necessary.
I think, look, it gives us at least a good insight in terms of what you do as an organization. The additional standards that you spoke about over and above the industry standards, can you just maybe give some example of some of them that you yourself, and I'm sure you would have done some research to have come up with those standards, Jan?
Yeah, the one that comes to mind first of all is on the polyethylene side. One of the tests required on polyethylene pipe, the OIT, oxygen induction time test. It's a quick test, small sample of pipe. It's put through special equipment, special procedure, and that material is going to last for a certain time before it oxidizes completely, etc.
Yeah.
We have found that requirement is too low for people that start off with excellent material, a P100 material, as was said. An accredited or certified P100 material, it is no problem. But where we sit with people that take chances, and unfortunately we can say quite a bit about that in South Africa as well. There's large quantities of redundant pipelines that get recycled and fed back into this process, which is not allowed in terms of the standards. And we don't allow that either. And coming back to the OIT test, the standard OIT test does not necessarily highlight the use of non-standard pipe. So we've upped that. We require of our members, whatever the figure is, I forgot for the moment, say a 30 minutes test. We require say a 50 minutes test on that. So things like that, again, we do too.
just to give that extra assurance on the quality that you would obviously then expect from the manufacturers.
Absolutely.
Yeah.
And that's
No, thanks.
we like to say that if you do a tender document, ask for tenders, one of the requirements, the 3 or 4 very good ones that you should include, one of them really is, I think it should start off with, it should be a SAPMA certified pipe.
Yeah, yeah. So I think you put your own little logo on the pipe?
No, that is.
Or is that with the manufacturer's certification from the manufacturer specifically?
You're talking about the Noble, the term.
No. You're saying now there's this SAPMA certified. Would that just mainly be the certificate that you give to the manufacturer?
Yeah, that's right. And
Okay.
that gets updated annually.
Yeah.
You can't.
Yeah.
Right.
No, I think that's quite an important thing. And look, myself, I've once I was a water and sewage technician designing major lines. Yeah, I wasn't even aware that at that time that you could ask for SAPMA certified. So it's good to know. I'm still learning, and I'm sure the colleagues online is a good point. So we've got a hand from Nokutala. I think let's take the hand from Nokutala. You should be able to unmute if you want to come through with your question. Thanks.
Thank you, Chair. Yes, thanks for acknowledging. I just want to find out from our colleagues here. Okay, maybe might just give my background.
Go for it.
I'm environmental specialist within TNPA. Thank you for this presentation about plastics and different types of plastics and how they are made use. But my question is that since you are making these plastics for usage anyway, for different usage, we might actually, all of us have heard, might have read, might have seen how much plastics actually ends up in the oceans and then choke the marine life. So I just want to find out as to, do you actually have any plans that you are having in place to make sure that we actually don't end up having the plastics in the oceans? And then maybe it might not necessarily actually be upon you at all to make sure that is actually done, but what measures or what education theories that you have, or what plans actually that you have actually or contribution to make sure that we are mitigating, and where we are not mitigating, but we've got ways to make sure that we are preventing such. Thanks.
No, thank you. So basically being a responsible entity to make sure that you also then take care of the environment as well. So yeah, I don't know. Katisa or Jan, I don't know who wants to take that question maybe.
I think let me Katisa can add in if he wants to.
Yeah.
Well, first of all, we should recognize the fact that on both polyethylene and PVC side, most of the pipe grade polymer being used in South Africa are manufactured in South Africa. There is a component or a certain portion that gets imported, and we recognize that it can cause hazard in the sea life where containers spill or whatever happens. We unfortunately have got no control over that. I mean, obviously. What we can do is within our borders where we have control, we do whatever we can. And I'd like to say that you would hardly ever see a piece of pipe alongside the road, discarded pipe. The price of polymer is so high these days that it's really golden lies out there. Every bit of pipe that gets non-approved or whatever, discarded or redundant, that gets recycled and fed back into one or other system. So in finished product, we don't have a problem whatsoever. With the polymer, with the small little granules, you're quite right, Noku. It could be a problem, particularly on the seaside or in the oceans. But there again, I'm afraid we take note of that, and we talk to whatever we can or whoever we can about that, but we don't have any physical control over that. Okay.
No, thanks. And maybe just to add on, I take it as part of your audits of your manufacturers, you would just make sure that they, option from their side, obviously don't contribute towards any form of pollution, something down that line.
Exactly.
Mm.
Part
No.
of the code of conduct that we.
Yeah. Make sure that obviously the companies are being ethical and looking after the environment as well. Katisa, I don't know if you want to maybe add on to the comments.
Yeah. We also have sister organizations like SAVA, which is South African Vinyls Association. We also have Plastics SA that also focus more on plastics in general, including those plastics that are used for packaging. In fact, those are the ones that you normally get in the oceans, causing pollution. And I know there's a big drive to promote circular economy. There are people who have actually been assisted to establish businesses. It's just that I gave away the shoes which were made, school shoes which were made. Someone gave me 2 pairs as gifts, and then I had to give them away to some children, made of PVC. So it's just that people are not aware that you can imagine you are ordering material from Sasol. Then it comes into your factory, and then you push it through your machine, and you consider that some of the material that has to be discarded, you consider it as waste. But you are forgetting that you've actually paid for it. So it's not waste, it's your resource. So once your mindset changes from someone who believes in looking after the environment, or being the how do you call it, the steward of the environment, anything that comes into your gate, you will see it as a resource, so you can make money from it. So I think what we need to do, maybe the whole country, is to assist people to help them see that anything that you buy, including stuff whenever you go and buy groceries, any packaging that comes into with that packaging, with the groceries, you've actually paid for. So it's your resource. So you can start separating waste in such a way that you can sell it to people who are recycling it and recover some of your money. Yes.
Yeah, no, definitely. So you ultimately responsible and accountable for the products you buy. So you need to then take that into account. Yeah, no, exactly. Okay. As we've got the hand now from Ndumiso. I think you should be able to unmute. You can come through.
Hi everyone. Nice presentation from Katiso. Let me introduce myself. My name is Ndumiso Mkwenya. I am a professional engineering technologist. And for me, it's not a question, basically. It's just a comment to say that was a nice presentation. And with plastic in abundance out there, and I believe us as engineers is a space we need to tap into. I believe there's a high value in plastic. So we should, not plastic pipes, but going beyond the spectrum of plastic pipes, considering plastics as well. I believe there's a huge market and a huge engineering development that might be done there. So I think it's an aspect that we engineers should tap into. And thanks.
No, thank you. So they're touching on obviously making use of plastics in other industries and fields. I know here along Gqeberha, you've got the walkway along the beach made out of recycled plastic. So I mean, there's this, lots of different uses. Yeah, I don't know. Katisa, do you want to comment on that by any chance?
No. That's what Ndumiso is saying is very true, and thank you very much for your kind words. In fact, how I came across plastics at Wits University, we had a course in construction materials, but we did concrete and modular ratios and those things, post-tensioning, everything. But then there was a component of it that looked at other materials that you normally encounter, which are paints, plastics, and everything. So I started hearing about thermoplastics then. Then when I started working, I used to work as an R&D, research and development engineer, and we were working manufacturing concrete products for a company that was owned by Avenge, and I used to go overseas to see like a lot of different things. And I saw at one factory they were making concrete on this side, and then they made PVC on the other side. And I went back asking my bosses why they are not doing the same thing, but they refused.
Yeah.
And I was saying I really don't see, because I don't see it as a chemical material. I see it as because chemical engineers are also the ones who are making steel, right?
Yeah.
They are also
Yeah.
running the places where they are manufacturing cement,
No. Yeah.
mixing
Mixing your additives, chemical engineers on the
additives.
additives.
Yeah, they are the ones who actually come up with those things. So in the same way, they are doing it on plastics. I don't see why we are not seeing it as our material.
Exactly.
I believe
Exactly.
it's just a matter of time. We just need to start seeing it as our own material, but we just have to be aware that its behavior is slightly different from these other things.
Yeah.
So
No,
whenever
thank-
we come across it, we handle it differently. And I believe there are a
Yeah.
lot of opportunities to solve a lot of human problems with plastic pipes in the civil engineering industry.
No. It's a mindset change. It's a mindset change. Just the way you look at things. Just need to think a bit
Yes.
more openly and then a bit more differently. I see we got Dumiso and Dumiso don't come through again.
As coming in again, I'm not seeing it as basically as a replacement of concrete, but I'm saying it can work in conjunction with
In
concrete.
conjunction. Yeah.
I myself, I have tried it back home. I've built a cow kraal.
Yeah.
I was tired of the logs, and that thing is strong. It's flexible to bend, but too strong for it to break. So with the combination of it, steel and concrete. So yeah.
Yeah,
So
sounds like you got a good business proposal for for the rural areas. No,
Yeah,
well
yeah.
done. You must maybe share that with us, and maybe we can do a presentation in the future just to show us your innovation as well in Daviso. Yeah.
Yeah.
okay, thanks.
Thank you.
So okay, so just another maybe more from a technical point of view, Katiso. So look,
Yes.
with what you showed us now in the presentation, the technical detail and like what you find is that in most cases, like on this designer side, they may not necessarily have the know-how or the understanding, because what we will see on our side, we get a technical manual. It comes from one of the Duraplastics or DPI plastics. We get the manual, open up the manual, we flip and we say, okay, here's the pipe size that we specify, and we carry on. But we might be missing a lot of technical details in that regard, because now what you are showing us is that depending on the type of application, and how long you want it to last, there's other design elements you might need to consider. So is there anything out there for civil engineers, from a I don't know, if like a course or something that can teach a civil engineer how to properly design and specify a plastic pipe for the application they're looking for? So I don't know if you have anything like that out there, Katisa.
I don't know if you can see my slide.
Yes, I can see the slide there. Yeah.
Yeah. So I was showing that we have this technical manual.
Yeah.
Yeah. So if you were to go, because some of the people who contributed in putting it together are actually civil engineers. In fact, Mr. Fenter, as the CEO of SAPMA, is a civil engineer.
Yeah.
So even Mike, who was supposed to present, is also a civil engineer. So you will see it actually talks to the civil engineer. The language in the technical manual is not so complex, even though they have also explained the chemistry of polymers and monomers and whatever. But you will see that it makes a lot of sense. They didn't go too deep into the difficult chemistry. So I would say the first point to start would be after this to download from the website, to download this technical manual. For people who are old school like me, you can purchase it at a price and start going through it. So there's one of the state-owned companies actually that has approached us with the same request for a course. So we are busy putting together something. So once it's ready, we will let you know.
No, that'll be great just to put it out there for the other civil engineers, because again, like I think when you started, not a lot of people, look too deeply into this. It's just that, you pull the manual here and you select a pipe and then you carry on. But yeah, look, I think maybe from what I'm picking up is that the degree of confidence in terms of the information that's in here, you've done your research, and then the information you've given it should at least save time, or from the end user side, doing too much research. But you've got the stuff, the work's been done, just apply the knowledge basically.
Yes.
Yeah.
Can I just
Yeah.
something?
So we're coming onto 1800 colleagues. So I think we'll look at maybe one or two more questions, and then we'll look at closing. So the one question I wanted to cover, Katiso, now a new growing trend is smart infrastructure, smart technologies. So are you as SAPMA looking at anything in the respect with IoT devices, maybe embedded in the pipe, so that you can do continuously, collection of data? I don't know if something like that's being thought of, or just give us some insight. What are you doing within the smart infrastructure space?
I'm actually very passionate about digitization and IoT. As SAPMA, I know we are not there yet, but we normally hold conferences every 2 years. So some of our exhibitors at the conference, because usually this is something that's done by people who are selling flow meters, because that's where you can actually put embed sensors and those type of things into the thing. Then you fit your the whole, if it's a flow meter or just a sensor or something into the thing. So I don't know whether it will be a SAPMA thing, or whether because you can also have suppliers of those people of sensors becoming members of SAPMA. But for materials, for those who are manufacturing, where I see the opportunities in exploiting this new technologies, you also have BIM for manufacturing, which is building information modeling for manufacturing. So I believe in the future we'll be able to do that and assist the member manufacturers to establish
streamlined production and all of that.
In production, yes. In such a way that when there's a pipe failure, you should be able to go back to your that information should be on the GIS. Whenever there's a pipe failure, you should be able to go directly back to the thing without having to go and read what's written on the pipe. So I see that as something that will be coming.
So there's potential for the future. I guess time will tell. Okay, no, thanks. So look, colleagues, will be looking to wrap up. If you have any comments, questions, then look, do drop it in the chat box. We also have now that the survey questionnaire that we shared. So maybe just as a closing comments for both Jan and yourself. So if you look at now one key message for our civil engineers, and I think as you can see online, we don't have any civil engineers. We actually have environmentalists as well. So it's a good diverse crowd. So just one key message that you can leave the audience, just regarding thermoplastic pipes. What would that be, Jan?
Well, first of all, I think I'd like to emphasize the fact that it's a material that will not go away. It's a modern material. An enormous amount of R&D goes into the materials. was referred to in the presentation as well, how the design stress have increased over the years in some of the material. So it's here to stay, and we're very concerned that about the lack of information, and that's why we try and interact. We're very limited with our resources, but that's why we try and interact and even design or publish the technical manual. So the message really is we are there to help. It's a non-profit organization. If you need any info other than what you have at the moment, please don't hesitate to contact us, and we will support as far as possible. Just quickly also take note that every second month we have a technical webinar, online seminar, and if you are interested in that, please send us your contact details, and we put you on the address list for that as well.
No, thanks for that. Yeah, no, definitely that will be quite helpful. Katisa, your closing shots, and I've got one question to ask you after that, just out of interest. Katisa?
Oh, asking me, okay. Yeah, so what I wanted to say about plastic pipes is that they are not just an alternative. They are the future, and we actually need them for its future of sustainable, efficient, and resilient water infrastructure, especially for a water secure Gauteng, because we are water scarce. So we need them like oxygen, not just as an alternative. So when we do our designs, as we have shown, we have to choose wisely and install them correctly. And in fact, I would say before you do a pipe project, maybe download the manual first, the technical manual. You will see it has all the information you need in there. Thank you very much.
No, thanks. And just the one question just out of interest, I was looking at your slides. You say no knee before 500 degrees. So does that mean when the pipe bends it, then it looks like a knee? You can just briefly explain. I found it quite intriguing.
Which one is that one?
No, there's a comment says I think when you comes to the testing of the pipe, it says no knee before 500 degrees. So I just out of curiosity, is that now a case when the pipe bends, then does it look like a knee if it bends?
Oh, yes. Okay, maybe Mr. Penta can also help me. If I hope I understand you well. So the knee, each material has a knee. On that regression curve.
Yeah.
There's a point when you are testing it where that the regression curve changes the slope.
Yeah.
So is
it the slope change that looks like a knee?
Yes, it's the slope change that looks like a knee, and that's how you determine the lifespan. I think.
Yeah.
I think that he can assist me if I'm not getting it right.
That's perfectly right. The knee only refers to the kink in the
kink in
the kink in the graph.
Nothing to do.
Yes.
Yeah. No, look, it's a very interesting term. I don't think I've seen that before, but no, it makes logical sense when you explain it. No, but thanks. So colleagues, I think, look, that's basically now the end of the session. I just want to thank everyone for joining today's SAICE Fireside Chat.